Our next presenter is Jeffrey Ichnowski, and he's going to be talking about cloud computing and how to share the planning computation load between local embedded computation and computation in the cloud.
Hi, my name is Jeff Ichnowski. I'm presenting my work with Jan Prins and Ron Altervitz on cloud-based motion plan computation for power-constrained robots. So I'm going to start off by motivating our problem. As many of us know, that motion planning is a computationally intensive process, especially for a high degree of freedom robots in cluttered environments. And if we want to get feasible solutions quickly or optimal solutions to a desired level of quality, we need a lot of compute time. And we want to do this on a mobile robot. So we have a problem. Mobile robots, if we look at their design, are fundamentally geared towards having extended battery life and low weight. So there's really not a lot of room or power for high computing power. So where are we going to get the computing power? And if you guess from the title of the talk, we're going to try to get it from the cloud. And for many of you, you're probably familiar with what the cloud is, but I just wanted to put up an example of how flexible and how convenient the cloud is for this particular problem. We want to use rapid provision of computing power. If we look at just what Amazon provides, we can get a 36 virtual CPU computer for $1.67 an hour. But the real power comes in if we just do this little thought experiment of how much does that $1.67 get us? Well, 1 hour on 36 virtual CPUs. But what about 1 minute? We could get 2,160 virtual CPUs for that same price. And if we say 1 second, we're now at 129,600 virtual CPUs for that same price. So if we have an embarrassingly parallel problem, why not just get it done as quickly as possible? So that's the power of the cloud computing that we're going to try to get to. Now, the thing I should mention is that there's no cloud provider that I know of that bills by the second. So this is a hypothetical for now, but perhaps not so in the future. So to classify our problem, what is each of the CPUs involved good for? What is the robot CPU good for? What is the cloud good for? Is what I want to focus on right now. Well, the robot's computing power is power constrained, and the cloud is just massive power on demand. But the robot has fast access and low latency access to its sensors and its actuators. Whereas, on the other hand, that network connection between the robot and the cloud becomes a significant bottleneck that we need to deal with. So the ideal task for each of these is, I would say that with the fast access to the sensors and actuators, we want to have the robot monitoring the sensors, the 60 frames per second that you might get, for example, from a video input. We want it driving the actuators in a hard real-time loop, and in general, we want it to be reacting to its environment. On the other hand, the cloud is really good for heavy computational tasks. But these tasks need to have a soft deadline. That means a deadline that they can miss. So we can't predict the amount of time that it's going to take. We can sort of estimate it, but we need to make sure that we are going to accept, with some acceptability, tasks that miss their deadline. This also means that we also have to have tasks with deadlines that are greater than their latency. So our idea is to split the computation. We want to have the cloud compute a roadmap for the robot, and we want the robot to use that roadmap to navigate around dynamic obstacles in its environment. So we come up with this workspace model where we divide the workspace into two classes of obstacles. There's the static obstacles and the dynamic obstacles. The static obstacles are things that do not change over the course of the task. These are things like self-collision, walls, floors, things that you might be able to get from an architectural database or even Google Maps. The dynamic obstacles are things that can move throughout the task. Those are things like people, cats, other robots. And so what we're going to do is we're going to put the static obstacle computation onto the cloud. We're going to have the cloud compute a roadmap around those static obstacles, and we're going to have the robot navigate the roadmap around the dynamic obstacles. So I'm going to show you a high-level overview of the algorithm. The specifics are in the paper. But we start off with the sense plan move loop. And in that planning portion, we have a roadmap, a graph that we're searching, and we're using lazy collision detection to find a plan that we're going to execute when we move around the dynamic obstacles. On the other side, the cloud is computing a roadmap for the robot using a highly parallelized sampling-based motion planner that's asymptotically optimal. So we need them to communicate together in order for the robot to be executing in the environment and the cloud to be planning for it. And that's where we introduce this part of the loop where the robot is going to be requesting an update for its roadmap. And it's going to be sending over information about the static obstacles. It probably only needs to do that once. And it's going to send information about where its goal is and its configuration, where it will be when it wants the roadmap back. So after that, then the cloud sends the graph back to the robot, and we've completed our high-level overview of the robot's algorithm. So each sense plan move loop, it's going to check for an update from the cloud. If it's there, it's going to update its graph. It's going to request another one. This happens quickly and asynchronously, and then it goes back into its sense plan move loop. So we want the cloud to respond in a time-bounded fashion, so we just add a little thing that says, let's time limit our computation. Let's keep on planning until there's time left. And in my scenarios, I would say maybe let's plan on the cloud for a few hundred milliseconds before it returns the results, maybe 500 milliseconds. So one thing that you might be noticing is we've got these red arrows back and forth. This is the communication layers between the robot and the cloud. And I've shown them as red arrows, but the bandwidth between them is limited. And so we want to utilize this bandwidth efficiently. So to that end, we observed that not all of the graph that we're generating with the sampling-based motion planner is useful. Some portions of it are more useful than the other. There's also the problem that if we send the entire graph, that will increase the latency just because of the bandwidth required to transmit across the line, and thus decrease the utility of the roadmap by the time the robot receives it. So our idea is only to send the portion of the graph that's useful, and that completes the algorithm on the high-level algorithm on the server side. So what are the useful parts of the roadmap? Well, we'd say that shortest routes to goal are probably useful. Reachability to the workspace as a whole is useful. And then routes around dynamic obstacles are useful. Now, to give the robot maximum flexibility to navigate around obstacles, we actually only need to give it a dense roadmap in its immediate vicinity. So it needs to be able to react for some temporal bound within its current configuration. It doesn't need to be able to react to dynamic obstacles that are very far away from its current state. So to put these parts into our algorithm, we start off using the incremental roadmap spanner from Dobson and Beckwith. And what this does is it creates a sparse roadmap that retains the connectivity and reachability of the workspace. So we use this to significantly decrease the size of our graph that we send to the robot. And then on top of that, we add a temporal maximum radius for which we will send the dense roadmap. So if the robot's at that orange dot, it's going to get a lot of options to move around dynamic obstacles that are within that temporal radius. So we put this all together into a working system with the fetch robot. Now, in this system, the fetch robot drives up to the table and it begins the execution of its task. And its task is to go from its driving up state to get to a pre-grasp state for the bottle. The static obstacles in this environment are the table, the self-collision, the office space in general. The dynamic obstacle is me being a nuisance to the robot with that too. So the system here uses an RGB sensor to detect the obstacle. In order to put this all together, though, we, into the simulation results, we simulate this so I don't actually have to stand there the whole time and do hundreds of runs of these. And so here's what the test setup looks like. With the fetch robot, it's got a 4-core Intel, and we're only using 1 core for the planning. The rest of the cores are being used for sensor processing and so forth. It communicates via HTTP over transport level security to a cloud computer that's located at Renzi, which happens to be 6 kilometers away from our lab, which gives us a really fast network connection, 100 megabits per second, 12 millisecond ping. And because of that, we're able to simulate, artificially slow down the bandwidth and latency to something we might see in a non-laboratory setting. So also just to mention that over these tests, we simulate the obstacle going back and forth, so to avoid introduction of any sort of bias as well. And what we are measuring is the total execution time. So what we're trying to do is improve from the time it gets to the table to the time that it reaches there, how fast can it be improved? And in this chart, you can see that the robot without the cloud is that top line. It gets about a little bit over 32 seconds for total execution time. If we introduce the cloud with some reasonable bandwidths and latency, those are the bottom 2 lines, we get a pretty significant improvement for just bolting on external compute power. On the other hand, if we have a really slow connection, that's actually probably slower than your mobile phone on the top there, and we have a high latency, we see, as you might expect, that if you can't reach the cloud quickly, you don't get much benefit out of it. And the reason why we get these speed-ups is because this is what the graph sizes look like at the end of the executions for those differing connection speeds. So with the better connections, the cloud is able to spend more time computing a roadmap and less time communicating it. The other parameter that we looked at was that Tmax and how that affects the overall quality of the solution. So if you recall, this controls how much of a dense radius versus sparsity of the graph is. And we're using, basically from our simulations, that cyan line across the bottom. And the purple line on the top is the completely dense roadmap. And putting that together, when we vary that parameter along the y-axis along the bottom, we can see that if we decrease it too much, we start to see an worsening execution time and increased failure rate. But if we increase it, we don't actually get much improvement beyond some threshold, which happens to be about 1 second. And we also get a worsening standard deviation. So the dirty laundry slide, so this is not relevant for all motion planning problems. In particular, if the static obstacles don't change from one execution to the next, just pre-compute. Other thing is the graph size just continues to grow over execution. So if you have a particularly long-running task, it's going to basically have problems with associated with searching a large graph. And I'll end it there because I'm out of time. Thank you, and any questions?
We've been assigned responders for every paper. So our first responder for this paper.
Hi. I liked a lot of your paper, especially in the part in which you solve technically the problem of motion planning using, extending PRM start with with the other spanner. And this is a good point, especially the dense and the space sampling. But there is one thing that I think should be discussed. You use the cloud only for static obstacles. So you left the dynamic obstacle to the local planning. Mm-hmm. So that means that local planning must deal with a lot of sensors, uncertainty. So you go farther than motion planning. I mean, you go toward the task planning more than only motion planning. So why cannot you use cloud also for this task and attach meaning in order to give semantics, to action, so goes toward the cognitive task planning, enriching the solutions of the problems? Because I fear in practical the local planning for dynamic cannot be able to solve a more complex problem than this one with only 1 degree of freedom for dynamic. Can you comment?
So if I'm processing the question right, I think one of the fundamental issues that we're tackling here is that the cloud has a long latency, and we need to be only giving it tasks with soft deadlines. I mean, the cloud could disappear, and we want to have it still have options to navigate its environment. So that's why we've got the sparse roadmap as well, is that even if the connection goes down, and we still have options to navigate the environment. But as far as in like general response to your question, if we give it we can give it any task that we want it to give it that has a deadline that is greater than that latency and has a soft deadline.
The last remark, just a suggestion. Why don't you cannot you wrote in the paper you can use commercial servers, the cloud. So for example, if you use a cloud lab in Minnesota, they have a lot of nodes, and also another point, they use ROS to access the cloud.
Mm-hmm.
You are using ROS only to control the robot. I think if you can use ROS to access the cloud, probably technically you can save a lot of time, and could become more efficient.
Is that more of an implementation idea?
Yes, it is a server, cloud server, with the 50,000 nodes, and you can access through JSON messages. So that will make much more effective your system.
Mm-hmm.
So we had a quick question. Well, maybe we can have the next speaker set up.
So it seems like a lot of the bandwidth considerations that you gave were just for transmitting the graph.
Mm-hmm.
But at the beginning of the problem, you have to transmit the sensor readings to the cloud in order to compute the static obstacles and whatnot. Did you consider the bandwidth requirements of the sensors as well? I mean, similar to the first question.
Sure. So in the implementation, there's an initial request that sort of starts the whole process, and that's where it says this is the static environment, and then the subsequent ones are just updating where the robot is at that time and where it wants that dense roadmap. So in a lot of cases, if you already have like an architectural database, like if we already had an architectural database of here, we could just say we're at this space and the server could load it up. I mean, that's another part of the cloud which I haven't really focused on, is the power to have large data sets there. So we could potentially access the static obstacles of an environment just by saying, here's my GPS location. Does that answer your question? Sort of, yeah.